Hey everyone, this is ThermoFluids Unlocked, and this is the first video on a series focusing on a very useful software for ThermoFluids application, specifically for handling complex thermodynamic properties by enabling us to easily calculate the thermodynamic properties of pure substance, and also enabling us to solve a complex set of thermodynamic equations later. So today I'm just going to start with the introduction of the interface of this software, which we call it the Engineering Equation Solver, also called EES. And we are going to know the interface, know the functionality of a few options of that as the starting point. And we will also try to look into two simple problems that we can either use these to find the thermodynamic properties or use the classic thermodynamic tables that we have available to show how easy can this software calculate these properties for us. So I will start with a concise overview of the options. The ones that we need for this video is to first look at this SI option. It basically enables us to choose the unit system that we are solving our problems in. It's in SI and there is no need to change it if we work with SI units. Specific properties, for example, volume, specific volume, or mass-based, so we keep it as is. Unit pressure, you can switch between kilopascal, bar, or even megapascal. For temperature, its default is Celsius. Sometimes in thermodynamics, we will need to go with Kelvin. So in some cases, we will need to switch it, but for thermodynamic properties, it's fine if you provide the input in Celsius. So what is important is that you as the user be aware of the default values of the default units of the variables that you have in your equations, so that you put the right number. So if you put a number and in its nature it's a Celsius value, and here the setting is on Kelvin, obviously the software is gonna assume that you have provided it in Kelvin. So it's really important that we set the right units for the variables that we provide for the software. So I'm not going to change anything, and I just click OK. And here, the other option that is really useful for today's video is this function information. You can see a set of functions, for example, related to mathematics, mechanical design, and many others. But the ones that we want to focus today is the second one, thermophysical properties. They are listed for real fluids. So if I want to simply define real fluids, is that we do not have a specific and known equation of states for those to relate PV and T so that we can easily use it. So either we need to rely on thermodynamic tables or use EES to find them. For example, it could be a superheated vapor in a high pressure. It could be the saturated mixture or a compressed liquid. The other item is ideal gases. And as you know, in ideal gases, we have the equation of a state. It's like for very low density gas, and we can use these as well for its thermophysical properties. We have air H2O, that is basically the humid air, and we will use it later if we want to look into ventilation problems and heating or cooling of humid air. You can also use it, but now I'm gonna stay here in real fluids and look at a few of the familiar thermodynamic properties. For example, here you see density, or if we scroll down, you see internal energy, or what we call energy in thermodynamics. It has the critical pressure of the material that we may need. Psat, which is the saturation pressure. It has quality, which is basically in a saturated mixture, the mass of the vapor compared to the total mass. Or it has T critical, which is the critical temperature. We have Tsat, we have the T triple point temperature. All of these are well known on the PVT surfaces of pure substance, and we also have volume. So basically, when you choose a property, and I'm going to stay with volume, then you need to choose the fluid. And I'm going to go down there and choose water. And as you know, water as a pure substance can exist in different phases. Either it can be a subcooled or compressed liquid. It can be in saturated form, a mixture of liquid and vapor, and it can be saturated vapor, just in a gas form. So if we know that our phase is in this mixture form, we know that T and P are not independent variables. And in that case, choosing them as the independent variables will not be correct. In my first example, I am interested in finding the properties of saturated water at a temperature of 100 degrees Celsius and the quality of 0.4. So I already know that it's a mixture. And I choose quality instead of pressure, and I simply paste. So now we have this function here. If we go and click on this check equation, it will check the number of equations and number of variables. And since now the number of equations is less than the number of variables, this problem cannot be handled by EES, because we need to provide two more equations, and those two more equations are basically the value of t and the value of x. So what I'm going to do, I'm going to make it a little bit look better. So I'm going to use these symbols to comment this line and hide it from the compiler. And I'm just going to name it as example 1. And then I'm going to provide T1 equals 100 degree. And I know that it's already in like Celsius, and quality of 0.1 is equal to 0.4, and we know that it doesn't have any unit. I'm going to name it V1, and T equals T1, X equals X1. By doing this type of indexing, I'm actually making arrays, and later we can keep many equations together and just change the numbers, and it's kind of the best way to use EES, but you can simply put T underline 1 or however you like. So the important thing is that EES has the same number of equations and variables, and in other words, in mathematical terminology, it is a closed problem. The other thing that I want to calculate is the pressure, and I already know that this should be the saturation pressure. So I scroll up, and here I choose saturation pressure, and as you can see, it's only a function of temperature. The changes that I need is to put the proper names and provide the proper input. Now, if we press solve button, it will solve this equation for us and list the inputs and outputs. And as you can see, X, which was the quality of 0.1, is provided, and T was provided, and it calculated the specific volume for us, and also the saturation pressure for this state. Now, let's take a look at how we can handle this problem with thermodynamic problems, thermodynamic tables. When we have the temperature and quality, we know that it's saturated state, so we go to the saturated water table. We choose the right row. It corresponds to a temperature of 100 degrees of Celsius. And obviously the pressure is equal to Psat at T equal to 100 degrees of Celsius, which is 101.3 kilopascal. This is a minor difference with what EES provided for us. And to calculate the specific volume of that mixture, we use this correlation, which in a way finds an effective specific volume for the mixture equals the specific volume of saturated liquid plus X multiplied by the difference between the specific volumes of saturated vapor and saturated liquid. And the answer is 0.6698 meter cube per kilogram. Again, you can see that there's a very, very minor difference between the values, but it's acceptable. So it's totally acceptable, and we could use both of the methods to find the properties if needed. Now let's go to example number 2. I'm just copying it to make things run faster. And example number 2, I have the P given an X, and this is again water, and this time the quality is 0.6, and I'm just taking care of the indexes. Here I just need to simply change it to P equals to P1, P2, and X equals to X2, and it asked for T. I can just go and paste the function for Tsat and paste it here, correct the naming, and hit the solve button. It says that the equation does not have an equal sign. So the software is smart enough to find some issues here, and I've simply forgotten to put this equal sign here. So if you see an error sometimes, it's probably coming from our side. So just look into equations and be open to handle problems like this. And now I solve it. And if I just make this table bigger, you can see that now it has found that the Tsat is equal to 99.61, and the specific volume is 1.017 meter cube per kilogram. Now let's look at the classic way of handling this. I go to the thermodynamic table. As it's saturated, I look at the saturated water, but I can go with the pressure entry to make things simple. At 100 kilopascal, I have the Tsat equal to 99.62, which you can see it's similar to what EES gave us. And I use the same averaging formula to calculate the effective specific volume for the mixture for this quality of 0.6. And the answer is really close to what EES gave us. It's 1.016819, and it's basically 1.017. So they're really close, and you're happy with this. Now let's go look at another problem, and I again copy it, name it example 3. Here I am going to give T to you guys, and it's equal to 10 degrees of Celsius. It's for a refrigerant, so normally in these type of fluids we are dealing with very low temperatures, as their name implies, and the specific volume is given, so it's equal to 0.02. The unit is meter cube per kilogram. We could just leave these units out. I'm just writing them down to just make it easier for you guys to follow. So what's needed is T and X. So here it is mentioned that it is saturated, R134A. So what they want from us is first the pressure. So I go here, choose Psat, and change the material to 134A. It should be here, yes. And I paste it. Just need to be careful about the names so that it takes the right input. And the other thing it was asked was the quality. So again, we have the quality function. It's here. And it says, okay, I need two independent properties. I cannot provide T and, for example, PSAT because they're not independent. But here I have the specific volume given to me. So I say, based on T3 and V3, find X for me. Again, the right names, providing the inputs, and this should be V. I don't know why I chose entropy, but it should be specific volume. So here, basically, I had to choose specific volume. So, but you could also guess the name, which is lowercase v, and you could just type it. And now I'm going to handle this problem with this, and it's given. So the pressure is equal to 414.9 kilopascal, and quality is around 40%. Let's look at the typical way of solving it with thermodynamic property of this refrigerant. They said it's saturated, so I open up the saturated table, look at temperature T equal to 10 degrees of Celsius, pressure is equal to PSAT, 415.8. It looks a little bit different from what is provided, but these kind of differences are okay in the context that we want. And later for quality, either we can use the mathematical relation between this effective specific volume of the mixture, and then find X as V minus VF divided by VFG, which is 0.39, and EES just gave the same number to us. So it's really faster, and if we provide the inputs carefully and the equations carefully, it can help us handle complex problems in easier way. Now, I want to look at a problem where if we use thermodynamic tables, we are going to end up with interpolation. Sometimes it could be a little bit time consuming, and we don't want to do that, so we can use these in those cases. So in example 4, the temperature is given, it's 0.2 degrees of Celsius, and also the quality is given. So I'm just going to delete this and type X4 equals 0.4. The material is water, and they have asked for P and V. So I'm just going to copy these equations that I have up there and just name it V4, P4, and then just change the numbers, basically. It took just a few seconds, and I solved it. And this is here. So V4 is equal to 0.6265, and P4, which is the PSAT, equals to 108.9. Now let's look at how we can do it if we go with the thermodynamic tables. So for example, in Sontag book, if we look at this table, which corresponds to saturated water, we don't have the entry for 102 degrees of Celsius. We have it for 100 and 105. So in reality, we have the temperature and pressure for these 2 points, and in reality, there is a function that connects these dots together. And if I want, for example, to calculate the PSAT for 102 degrees of Celsius, I need to know that function, and I don't have it in thermodynamic tables. So what we do, we instead say, what if we assume that here we can actually have a linear form of function between these 2 points and find an approximation for the pressure corresponding to temperature of 0.2. This is an approximation. It really works if you have just access to thermodynamic tables, and there's no other way that you can handle this. And as you know, we know the formula for a straight line passing through 2 points, and we know that the slope is fixed, and based on that we can calculate the pressure corresponding to point 0.2. Basically, we need to construct two fractions between delta p's and delta t's, and I can write that fraction between point 1 and 2, and also I can write that fraction between the point that I don't have the value of p for it, like the unknown p, and either point 2 or point 1, and then p comes out as 0.9.1. The challenge is that when you want to calculate the effective specific volume for such a mixture, you have to repeat this process for the specific volume of saturated liquid at 0.2, at 100.2 degree of Celsius, and you also need to repeat it for VFG, which is basically the difference between specific volume of saturated vapor and saturated liquid. So you need to do 3 interpolations in this problem in total, and just 2 to find VF and VFG for 102 degrees of Celsius, and then use that correlation, which is VF plus XVFG, to find the effective specific volume of the mixture, which is 0.62, and EES just gave it us in a second. Now, let's look at the final example where we should be dealing with a superheated vapor case. So we have P and T given, and we want to find a specific volume. I can just again copy a few of these equations. So T5 is given to us, it's equal to 300 degrees of Celsius, and P4 and P5 is given to us. Then we have these two, it's 1 megapascal, so I need to convert it to kilopascal. I need to be careful because I have set kilopascal as my pressure unit in this problem. And they've asked for specific volume. I put 5, simply 5, and simply change it to P equals P5. You know, in many of these variables, we can guess what EES is naming that variable for us, for example, P, T, or V. But if you're unsure, you can just go into the function tab and just paste it. When I have T and P, I know that they're independent only in the superheated region and also in the compressed liquid region. So if I'm looking for a specific volume with these two, here I just click, and at 0.5, you see it didn't give me any quality as I didn't ask, so it's empty, but it's here. 0.258 is my specific volume. Now let's see if I do it with the thermodynamic tables. First, I need to go to saturated water table, as we always do. At a temperature of 300 degrees of Celsius, the sat pressure is nearly 8.5 megapascal. If I look at the PV diagram at a constant T, I can see that in cases that the given pressure, 1 megapascal, is smaller than P sat at the very same temperature, if we just hit the horizontal line to that curve, to that red curve, we find a point which lies in the superheated vapor region. So now we need to go to the superheated vapor tables and look at the corresponding pressure, and then take the specific volume, which is 0.25794, which is basically given by E. Thanks, and this is the end of this video. Next, you can use these for handling the key fundamental governing equations in thermodynamics, including conservation of mass, first law, second law, and apply all these 3 to simple thermodynamic systems or complex cycles and assess their performance, efficiencies, and see how we can improve them. So subscribe to get the updates and know about new videos coming on this series.